Hey, what's up everybody? Who is ready for a thriller of a free response? It's a doozy. All right, as you take a look at this free response question, you are given an equation, and then you were told to determine the molar mass of an unknown metal M, a student reacts iodine with an excess of the metal to form the water-soluble compound Mi2 as represented by the equation above. Whew, okay, this equation is making more sense. I wasn't sure if there was an element M or what. So just some unknown metal. It says the reaction proceeds until all of the iodine is consumed. The aqueous Mi2 solution is quantitatively collected and heated to remove the water, and the product is dried and weighed to constant mass. The experimental steps are represented below, followed by a data table. All right, now I suggest you take a moment to look over the image here and the data table because there's a lot there. Part A says, given that the metal M is in excess, calculate the number of moles of I2 that reacted. Okay, so we're looking for number of moles. We are given mass values here in our data table. I'm going to start with the mass of the beaker, metal, and iodine, which is 127.570 grams. That's the mass of beaker, metal, iodine. I'm going to subtract from that the mass of the beaker and the metal. So I'm going to get minus 126.549. The difference between those two then is going to be the mass of just the iodine. Quick trip to the calculator. 127.570 minus 126.549 is 1.021 grams of iodine. Feeling good about myself, but remember it asked for moles, so I'm going to take that 1.021 grams of iodine and convert it to moles. 1 mole of iodine has a mass of 253.82 grams. I just took my handy dandy periodic table, found iodine, multiplied it by 2. Boom. My number of moles to 4 sig figs, 0.004023 moles of iodine. Boom. Part B. Determine the following for the unknown metal M. Subpart I. Calculate the molar mass of the unknown metal M. All right, now let's go back and think about what we just did in part A. We determined the number of moles of iodine. If we take a look at the equation that we were given initially, the ratio between iodine and the compound formed between iodine and our unknown metal is 1 to 1. Now, what does that tell me here? If I use 0.004023 moles of iodine, that means I must have made the same number of moles of my compound. Now, if I know how many moles of my compound I have, and I know that the mass of the compound formed is 1.284 grams, I can determine the molar mass of my compound. By taking that mass of the compound, 1.284 grams, and dividing it by the number of moles, I get grams per mole, or the molar mass of my compound, Mi2, which in this case is 319.2 grams per mole. Now, keep in mind we're asked to find the molar mass not of the compound, but of the unknown metal. So let me clarify that this is the molar mass of my compound. If I take that molar mass, we know that the compound is made up of 1 mole of our unknown metal M and 2 moles of iodine. So if I simply subtract the molar mass of 2 moles of iodine, which is 253.82 grams, I can deduce the molar mass of my unknown metal M is 65.4. Molar mass of unknown metal M. Whew. Subpart II. What is the most likely identity of the unknown metal? Well, now that I have a molar mass, where could I find a list of metals and their corresponding molar masses? The periodic table. So I scan my list of elements. I'm looking for a molar mass of approximately 65.4. Zooming in here, zinc is probably my best option with a molar mass of 65.39. We're just asked to identify it, so I'm not gonna go crazy here. I'm just gonna say zinc. Boom. Easy point. Subpart I. Calculate the number of moles of unknown metal M that reacted. All right, so we know that we formed 1.284 grams of our compound. And we know from part A that 1.021 grams of that 1.284 grams is iodine. So if we're trying to figure out moles of the unknown metal M that reacted, let's just take the mass of our compound that formed, 1.284 grams, subtract the mass of iodine that reacted, 1.021 grams, calculator it, 1.284 minus 1.021, answer, 0.263 grams of zinc. Careful though, we're asked to determine number of moles, so I'm going to take my mass in grams and convert to moles. Now, I determined the molar mass earlier in the problem, 65.4. You want to make sure that you're going to use the molar mass that you calculated earlier in the problem, which should correspond to subpart II. So divide my mass in grams by the molar mass, 65.4, to get me 0.00402 moles of zinc. Boom. Part C says provide a calculation to confirm the empirical formula of the compound Mi2 based on the data shown. Now, as you think about the definition for empirical formula, it's a ratio. The empirical formula is the smallest ratio of moles. Well, we just determined that our moles of zinc is 0.00402, and we know from earlier in the problem that we reacted 0.004023 moles of I2. Now be cautious here. If I have 0.004023 moles of I2, notice that for every 1 mole of I2, I have 2 moles of I. So I really have 0.008046 moles of iodine. So if I'm trying to confirm the empirical formula, I'm trying to confirm the smallest ratio that exists between zinc and iodine is 1 to 2. And I do that simply by dividing each of them by the smallest molar amount, which in this case is 0.0402, which will give me exactly 1 here and approximately 2 here. So my ratio is 1 to 2. And then finally, part D. If the student failed to heat to constant mass, would the calculated molar mass of the unknown metal M be greater than, less than, or equal to the actual molar mass? Explain. Again, when you're asked questions like this, you want to think about what measurements were made and how did you make them? So let's go back to B part I and think about how we came up with the molar mass of 65.4. We took the 1.284 grams, which was the mass of our compound, and divided it by the moles of our compound, 0.04023. And this question is saying, what if we didn't heat it to constant mass? As you look at the data table, you're shown 2 weighings, and the mass remains unchanged, indicating that it was heated to constant mass. But if it wasn't, if there was water mass still left behind, how would that affect the molar mass? So let's say we didn't heat it completely. This mass would be higher, maybe 1.584 grams. So our numerator would be higher. The denominator would stay the same because this number of moles of our compound was determined from the number of moles of iodine. So if our numerator were to get larger here, the denominator were to stay the same, the molar mass of our compound would increase. It would be greater than what it actually should be. And if our molar mass of our compound is larger, again, we'd be subtracting the same molar mass of iodine, we would get a larger molar mass of our unknown metal M. So a lot of times on questions like this, it's important to go back to the problem earlier in the problem where you actually calculated the thing that you're being asked about and think about how the measurements you made would change given the conditions you're provided in the question. So let's answer this. Molar mass of unknown metal M would be greater than the actual molar mass. Boom. Okay, so we've answered the question, greater than. Now we need to explain. Again, directly reference back to B part I. A larger mass value of Mi2 due to water would be divided by the same number of moles. Subtracting the molar mass of I2 from this larger molar mass of Mi2 would result in a larger molar mass for unknown metal M. Boom!